Hello and welcome back to Physical Geology. So I want to talk about Chapter 1 today, and Chapter 1 deals with the Earth in context, and it kind of starts off as kind of making some observations about our planet and our solar system and the universe at large, and then it'll answer some of those questions by looking into the Big Bang and then the solar nebula hypothesis. So we always ask, where did we come from? How did the planet form, and where did the atoms come from? And really we can answer those questions by looking at cosmology. And remember, cosmology is a study of the overall structure and the history of the universe. Now, in the early models, really put by an Egyptian mathematician who by the name of Ptolemy. And Ptolemy was curious about, and not just Ptolemy, but the Greeks were curious about how some stars stayed fixed, and they call those stars, and then some stars moved around in the heavens, and the ones that moved around, well, they called planets, right? Because the word planktos means a floater or wanderer, so planets were moving around. And so, but one of the problems they had was that the inner planets, Mercury and Venus in particular, kind of started moving backwards, had this thing called retrograde motion. And so it was really confusing. So Ptolemy devised some mathematical equations to kind of answer those questions. They weren't quite correct, but in the Middle Ages, church leaders took those calculations and the idea that Earth was in the middle of the universe, and they call that the geocentric model, right? So this geocentric model, and then that everything else revolved around it, right? And so we know that that's not really correct, and that was really disproven by studies in the Renaissance, mainly by Copernicus. You've probably heard of Copernicus, and also Galileo, and then some of the equations by Newton in the 1700s really figured out how the planets orbit and gravity. So in the model that Copernicus put forward in the early 1500s, late 1400s, was this model of the heliocentric, right? So the heliocentric model is the one where the Earth is just a planet that orbits the sun. So the sun in this case is the center of at least our solar system, right? Now, when we look at deep space, other observations we make is that we see galaxies. And galaxies, in fact, here we have over 100 billion galaxies that we can see. And each one of these galaxies has anywhere from 100 billion to 300 billion stars, right? So there's just an enormous amount of stars out there. And the key thing about all these stars that comprise these galaxies is that they're composed primarily of hydrogen, because hydrogen is one of the main chemical elements of our universe. In fact, even today, most of our universe is hydrogen. There's very little of anything else. Hydrogen and helium and these light elements. To make heavy elements, that has to occur in a different fashion. Now, the Milky Way, we live in a galaxy, and so in fact we live on a spiral arm about 2/3 of the way out. And so when we look up to the sky and we can see the Milky Way in the sky, we're looking out into the disk of our galaxy, right? Now, other parts of our solar system, note that we have the terrestrial planets. So I want you to know that the terrestrial planets are the rocky planets: Mercury, Venus, Earth, and Mars, right? So those 4 planets. And then we'll have this asteroid belt, and then beyond that we're going to have the gas giants. These planets are primarily made of frozen gas. They're quite large. And then as we go beyond here, we don't see it, but there's another belt called the Kuiper belt farther out. I think there's a question on one of the quizzes that you take asking about the Kuiper belt. So in this picture, we can't see the Kuiper belt because the Kuiper belt is so far away. And even beyond that, really the outer edges of our solar system is a region called the Oort cloud. All right, so that's our solar system there. Now, well, how did it all form? And so we'll talk a little bit about the Big Bang. And one of the things that Hubble, Edwin Hubble in the 1920s, noticed, he was an astronomer looking out at galaxies and stars, and he noticed that whenever he looked at distant galaxies, that the light coming from those galaxies seemed to be shifted to the red. And what I mean is that light travels in waves, and there are shorter wavelengths and longer wavelengths, right? And so on the spectrum, you've probably heard of this. You've probably heard of Roy G. Biv: red, orange, yellow, green, indigo, violet, right? Well, there's blue in there some, but those are the colors of the rainbow, right? So Roy G. Biv, yeah, B for blue, then I for indigo, and V for violet. So the blue end of the spectrum are shorter wavelengths, right? Like you would see here, shorter, more compressed wavelengths, whereas the red end of the spectrum are going to be the longer or more drawn out waves, right? In fact, if you think about the electromagnetic spectrum, we only see a very small part of it called visible light, and those are the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. But then if you go to shorter wavelengths than violet, then you have ultraviolet or UV radiation. Then there's X-ray radiation, right? Those are really small. But if you go to the red end of the spectrum, then just beyond that, what we can't see but we can detect is infrared radiation. So that's not visible to us, but it's another form of energy, right? And then there's microwaves and radio waves that go even farther than that, right? So the analogy about this Big Bang hypothesis, right, that was put forth by physicists is that it's because the galaxies are moving away from us, then they must have started at some geometric point, and we're going to call that singularity, right? This all mass is in one infinitesimally small geometric point. Now, so there are two lines of evidence that support the Big Bang hypothesis, right? One are these redshift calculations, which I'll talk about. And the other one is that wherever we look in the universe, and we could look to deep, dark spaces where there's nothing, but we still sense energy. There's this pervasive background radiation that just permeates the universe. It's about 2 degrees, a little bit more than 2 degrees above absolute zero. So that background radiation is the vestige of the Big Bang. It's still that energy that's around from this Big Bang, right? So let's look at this redshift calculations. And so the idea is that light coming from stars, the stars kind of absorb some light and radiate some light, and the light can be, or the energy can be manifested in these by these wavelengths, right? It's going to be these different wavelengths. And so light coming from our nearby star has this pattern of wavelengths, right? When we look at that same light from a more distant star or a distant galaxy, we see that the same patterns that we detect from our sun are also present from those distant galaxies. But note that their patterns are shifted to the right, which means that, well, at least it's interpreted that these galaxies are moving away from us. And so that Doppler effect is what's shown here. So when a train is moving toward you, you hear the higher pitch, but then as it moves away from you, you hear that lower pitch, right? So that's the idea. And in fact, I made a little video here. Let's check this out that I made, and we'll see what I have to say here.
To demonstrate the Doppler effect using this instrument that produces a sound, and as I spin it around my head, I want you to listen for the sound waves to compress or a higher pitch as it's coming toward you, and as it swings around away from you, you should hear a lower pitch, meaning that the waves are going to be of a longer wavelength here. So we'll start this here, and I'll start spinning it here. All right, we'll stop it there. So hopefully you would have heard the higher pitch sound moving toward you, lower pitch moving away. So that demonstrates this Doppler effect. Now the next thing I want.
All right, so now we've seen how the Doppler effects works, right? So now, and here's a little bit more that your book talks about it as well. So again, the compressed lights mean blue light, but obviously we see the red spectrum, which is kind of like this waves leaving, away from us. So we have the red light frequency here. No, so all galaxies are observed to have a red shifted light, which means they're moving away from us, right? So that's the redshift calculation there. Now, again, we talked about Edwin Hubble a little bit, and so he noticed this. So he concluded in 1929 that everything's moving away. And so the analogy here is like we had a clump of dough with raisins in it, and if we baked it, the bread would expand and every raisin would move away from each other. In this case, the raisins represent galaxies, and so they're all moving away from them as the bread expands, right? So that's the analogy there, this great expansion. So this Big Bang Theory proposes that all matter was at this single point, right? And then this expansion, and really they call it an inflation event, within a few seconds, the universe went from this point to something over 53 million kilometers in diameter, according to your textbook. And then it was incredibly hot, right? Incredibly hot. So at some point, we start forming very light atoms. That's hydrogen atoms, right? So the hydrogen atoms, and then they might combine to form some other atoms like helium, beryllium, lithium, or boron, really light elements, right? And so your book talks about this, the first formation of atoms, of these only light atoms, as the Big Bang nucleosynthesis. So that's, I think, one of the questions they ask about. And then as we go on, some of these hydrogen atoms, especially, because that was about 99.9% of the matter of the atoms in the universe just after the Big Bang, these started to coalesce, gravity brought them together, and gravitational energy converted to thermal energy, which means heat, right? And we talked about thermal energy, and that's how some of the first protostars. A protostar is a star. It's not quite a star, but it's becoming a star. Eventually, when it gets to a higher temperature, in this case, past 10 million degrees centigrade, then we start fusing together that hydrogen. And so the key thing about stars is that they can do nuclear fusion. So this takes place inside of stars, nuclear fusion. And the idea is you're taking lighter elements like hydrogen or helium, and you fuse them together to make heavier elements, right? And only stars can do that. Only something hugely massive like a star can do that.